All right, hi everyone. Welcome back to the Graphs and Matroids seminar. Today we have our own Amena from University of Waterloo who's going to be talking about edge-disjoint, linkage, and infinite graphs. Go ahead, Amena.
Thank you. It doesn't change the page. I don't know why. Oh yeah. Okay. I'll just Okay. I was trying to move it one after the other. Okay. So the beginning is conjecture of Thomason from 1980, and the conjecture says that edge connectivity of K for odd K is enough for a graph to be weakly K-linked, and weak here means edge disjoint as opposed to vertex disjoint, which is a stronger type of connectivity. K-edge connected means that I cannot disconnect the graph by deleting less than K edges. And equivalently, by Menger's theorem, it means that between any two vertices, there are K edge disjoint paths. So the conjecture says if this type of connectivity is achieved, then the graph is weakly K-linked, meaning that between any, if I'm given any K pairs of terminals, not necessarily distinct, like this, S1 and T1, and S2 and T2 up to Sk and Tk, then I can find a path from S1 to T1 and path from S2 to T2 and so on, such that those paths are edge disjoint. For even K, a connectivity of K plus 1 is necessary, and it's enough to prove the conjecture for odd, because if K is even, then K plus 1 is odd, and then by the conjecture for odd numbers, it is K plus 1 weakly linked, and so K weakly linked. So the best result until now for finite graphs is from 1991 by Hook, and it's just one step away from the conjecture. I will be talking today about this conjecture in infinite graphs, and I'll begin with the result of Oak, Richter, and Thomason from 2016. It's for one-ended locally finite graphs, and it says that there, for odd K, also a connectivity of K plus 2 is enough to be weakly K-linked. Locally finite means every vertex has a finite degree, and one-ended means I have one direction of infinity. So all the rays in the graph have infinitely many vertex joint connections between them, so they are together forever, as illustrated in this drawing on the right. Or more precisely, the deletion of any finite set of vertices leaves only one infinite component. I will try to reduce this condition of being K plus 2 edge connected to K plus 1. But let's first look at the proof of the result of Oak, Richter, and Thomason. So we have a finite set of terminals, and the graph is one-ended and locally finite. So they made use of what they call a standard fact of infinite graphs. And they found a set S, also finite, containing the set of terminals such that each edge coming out from S is the first edge of a ray, and this set of rays is edge disjoint. If we contract this infinite side and then have this finite graph, the contraction doesn't affect edge connectivity, so this graph is K plus 2 edge connected. We can first find the linkage in this finite graph by Hooke's theorem, which only needs K plus 1 edge connectivity, but if we just do this way, it will not work, because as you see in the picture, if we have a path that goes through the green edges, goes through this green edge, come back on this one, and a path that goes through the red edges, then when we come to expand it to, or try to extend this linkage into a linkage in the infinite graph, maybe we will have to use the same edge twice, the same ray and the same edge twice, if we have connections of this type on the infinite side. So one shouldn't just find a linkage here first and then try to extend it. What Oak, Richter, and Thomason did is that they first, before finding this linkage, they paired the edges incident with S in a useful way. And for this, they needed to do something called lifting. So this is lifting, this operation. If delete the two edges incident with S and replace them with this, an edge between U and V. And not any lifting, that is what they did, but good lifting that preserves connectivity in the graph below of the finite graph. So we wanted to keep the number of edge-disjoint paths between any two vertices other than S to be like the same. That doesn't go below a certain connectivity. For them, it will be k plus 1. But here in the definition, I'm writing k. So we say the pair is k liftable if after doing the lift, still there are k edge-disjoint paths between any two vertices other than S. We don't care about S. And the good thing about lifting is that, as you can see easily, if we find a linkage in the new graph after doing a lift, then there is we can return it to a linkage in the original graph. Just going through this edge, then go through those pairs of edge. Okay, so what they did is that they did successive lifting of pairs of edges until all the edges were lifted, and for this they needed the degree of S to be even. And also, as I said, they didn't just lift any pairs of edges, but ones that keep good connectivity for the finite graph that resulted from contraction. And also they wanted those pairs of edges to be linkable on the infinite side. And this linkability is achieved through something called the end graph. So here this picture summarizes what happened in the proof. So the end graph is defined like this. You can look at the arrays here, the green ray and the orange ray. There are infinitely many disjoint connections between them that don't mess with anything else. But the green ray and the pink ray, the connections between them have to go through the orange ray and use edges from it. So this is, so the pink and the green one are not adjacent in the end graph, while the green and orange are adjacent in the end graph. Again, they contract this side. They have this finite graph below. They lift pairs of edges that are keep connectivity good for this finite graph, but are also the first edges of two rays that are adjacent in the end graph. So they have infinitely many connections between them that don't intersect in edges any other rays that are going to be used, and don't intersect any finite construction already made, like the blue and red construction. But of course, after, say, if we made the blue construction first, then the red construction can go through the ray that had part of it in the blue construction, because it has already been used. So the pair of edges being liftable, this is captured through something called the lifting graph. So we want a pair of edges that's adjacent in this lifting graph, L of G contract G delete S, and S and K plus 1. The definition of the lifting graph for G, S, and K is like this. So two pairs of edges incident with S are adjacent in the lifting graph if they are K liftable. Back to the previous picture. So they choose pairs of edges to lift that are adjacent in the lifting graph and are also adjacent in the end graph. How did they know? They can find a pair of edges that does both things. So they first proved the theorem about lifting graphs. And this is the part of it that they used, that when the degree of S is even and the connectivity is even, the lifting graph is a complete multipartite graph that's not a star, and specifically the property they used is that its complement is disconnected. So when the complement is disconnected and of the lifting graph, and E, the end graph that expresses linkability between the rays, it's a connected graph. E is always connected because this is one end. So there are infinitely many vertex disjoint connections between things. So E is connected. If the complement of the lifting graph is disconnected, this means there is to things adjacent in E that are also adjacent in L. And this is how they found a pair of edges whose rays are adjacent in the end graph, but are also liftable or good for connectivity in this graph. So this is how their proof goes. Now let's talk more about the lifting graph, because, okay, there is something I should mention here. They wanted to lift all those edges incident with S to be left at the end with K edge connected, K plus 1 edge connected graph. So they had connectivity K plus 2 at the beginning, but to be able to lift all the edges, they needed the degree to be even, and also to use the theorem about lifting graphs I just mentioned. So they deleted an edge in case the degree of S was odd or the size of this cut was odd. They deleted an edge, and this reduced the connectivity from K plus 2 to K plus 1. And then after they lifted all the edges, this graph is K plus 1 edge connected. And by Hooke's theorem, there is a linkage, and also this linkage is good because we chose the pairs of edges to be good on the infinite side to be linkable. So we need to know what to do when the size of the cut is odd, or when the degree is odd. What happens in the lifting graph when the degree is odd? They already knew a few things about the lifting graph when the degree is odd. So this is a summary of all what they knew about the lifting graph. They proved it has at most 2 components. They proved that when the degree is odd and it consists of 2 components, the lifting graph consists of 2 components, then it's an isolated vertex plus complete multipartite. But they didn't know what happens when the degree is odd and the lifting graph is connected. And if the degree is even and it has 2 components, then they showed that both components are complete multipartite. When the degree is even and the connectivity is even, this is what they used, that the graph is complete multipartite. They didn't know what happens when the connectivity is odd, and they proved it's not a star if any component whose size has at least 4 vertices is not a star. They proved this by induction on the number, by induction on the degree of S. So let's look at some of the base cases they found. So here you see the isolated vertex plus complete bipartite, but through the induction, they just wrote complete multipartite. The property of being bipartite didn't carry over through the induction. Here is complete bipartite, K2 and 2. I have question marks next to the other graphs because the specific properties of those graphs didn't carry over through the induction. So here you see this is a graph with a lifting graph that comes from degree S being odd 5. It's connected. It has a specific structure, complete bipartite, but at the final result in the statement of the theorem, when it's connected, they didn't say anything about it. Here also, there seems to be a structure. It looks like a matching, but this is not the right way to read this. It's something else, the one on 4 vertices. Also, this kind of structure didn't appear after the induction was done again. And similarly for the thing below here. It's like a bipartite graph, complete bipartite, delete an edge. But this is not the right way to read it either. We should read this differently. Okay. So I claim that actually without induction, one can prove that all of those specific properties carry over, and they actually with the same proof they used at the base case works. Nothing new, like exactly the same proof they used at the base case works in general. And we can prove that we will have a complete bipartite graph, so that's like this, just the 2 sides differ by only 1, or isolated vertex plus balanced complete bipartite or complete multipartite. If you remember in the result here, they just said isolated vertex plus complete multipartite. So even induction didn't even help to keep with bipartite. They had to write something more general like multipartite. So how do we, or how does the same proof work? Let's look again at the base cases and look at them again. So what do you see here? What are the most important objects here? It's the, okay, maximal independent sets of the lifting graph. Okay, so let's read the results again in terms of maximal independent sets. So complete multipartite means that maximal independent sets are disjoint, pairwise disjoint. This isolated vertex plus complete bipartite means I have two maximal independent sets that intersect in exactly one vertex, and they are both big of size, almost half the degree. This, I told you, it's not the right way to read it. It's not that it's a matching, it's that it's the maximal independent sets make a cycle. And here the maximal independent sets make a path. So all this will be generalized or proved in general for big numbers, not just 3 or 4, not just 4 or 5. There are 3 important parameters in the proofs. So you might have noticed this already. The parity of the connectivity, the parity of the degree, and the upper bound on the sides of maximum independent sets. Actually, this is the maximum possible size of an independent set in the lifting graph. Ceiling of half the degree. I shouldn't write about here. I should say below or equal to this. It's by a theorem of Frank from the early 90s. The maximum possible size of an independent set in the lifting graph is this. When there are 2 sets of this size, it's with odd degree. This is what gives us the isolated vertex plus complete bipartite. So here's a summary of the new things about the lifting graph. So either complete bipartite like this or isolated vertex with complete bipartite. That's when the degree is odd and we have an independent set of this size, or when the degree is odd and the connectivity is even and any maximum independent set has at most size the floor of half the degree, then it will be complete multipartite. This will come from the even connectivity. And if K is odd, and we negate this part, the first one, so this or that, then the maximal independent sets will be any 2 of them will either intersect in one vertex and or be disjoint. Again, it's the same proof that they used at base case 5 and 4, which just works. So the proof involves something called danger set. So this is when things are not liftable. So if this set of edges F is like that, no pair of edges in it is liftable, then, okay, see the 2 dashed edges. If I lift this and have the green edge now, this will reduce the size of the cut formed by A by 2. So if this cut has size at most K plus 1, it will now, after the lift, become K minus 1 at most. And this is bad. This doesn't preserve the connectivity or having K edge disjoint path between any two vertices other than S. So this is where this equivalence comes from. This is not very accurate, but I just said this is not the proof Okrika and Thomason made. It's more complicated than that, but this is the idea behind it. So if no 2 edges here lift, their end vertices should be contained in a set A that's dangerous in the sense that it's separating and has the cut it makes is of size at most K plus 1. This will be used a lot and was used by them in the proof at the base cases at 5 and 4. So we have independent sets, they might intersect. We take dangerous sets corresponding to those independent sets. Here's A1 and A2, dangerous sets corresponding to two independent sets. I'll assume that S then this, so here, this is one independent set that's size K1 plus K3, another independent set of size K2 plus K3. And there are things outside, S sends things outside, because this is where we use the assumption or the upper bound on the size of the maximal independent set in. So if they aren't two maximal independent sets, both big of size, ceiling half the degree, if this is not the situation, then there are still things outside of them. The only case where everything is contained in two maximal independent sets is when both have size ceiling of half the degree. So if they are not like this, and this was the case of isolated vertex plus complete bipartite, then there are things outside, and this will be used now to find this lower bound here below the last lower bound. Upper bounds come from being dangerous. So at most K+1 edges coming out from A1 or A2. And so when we subtract the edges coming from S, we have this in G delete S, those upper bounds. Lower bounds come from the connectivity, because the number of edges coming out from each set here should be at least K edge connected graph. The lower bound here comes from that we took two maximal independent sets, and they are different. So their union is not independent. And so the union of A1 and A2, the two dangerous sets, should not be dangerous. And since it's separating, there's something outside it. It has to be, the number of edges coming out from it has to be at least K+2. And when we remove the things that are coming from S, we have this lower bound. Now, so this was done with sets of size 2 in the base cases of that was done in Oak-Richter and Thomason. But they weren't probably thinking in terms of maximal independent sets there. They were just trying to do the equivalent statement to being complete multipartite, which is that non-adjacency is an equivalence relationship. So they took something like an edge E0 that's not liftable with E1, and E0 is not liftable with E2, but E1 is liftable with E2. And number 2 there was nice because it's actually the half the degree almost. But one shouldn't think of this statement of that's equivalent to being complete multipartite when doing bigger numbers, even though it's true. The statement that's two things are not adjacent, but the two non-adjacency and one adjacency. One shouldn't be thinking of this because it will not be helpful with big numbers, even though it's true, because number 2 is not special there. So one should be thinking of terms of maximal independence. So now they will, the upper bounds and lower bounds here, I'll do as what they did in the proof, use it in this equation. This is a standard equation. So this notation means that something comma something means the edge is going from this side to that side. This equation is very easy to prove, and it's not graph theory, like just sets, counting things between sets, and substituting things into this equation gives this upper bound, this lower bound, and so this has to be non-negative, and this means that K3, the number of edges going into the intersection, has to be at most 1. So this proves that the intersection has to be of any two maximal independent sets has to be at most 1. So note that up until now, so here, up until, oh, sorry, we didn't use any parities yet. Okay, now when we assume that this is 1, assume that there is actually an intersection. This will make this 0. This will equal this. The upper bound will equal the lower bound in that case, if there is an intersection. And this will force all the individual upper and lower bounds here to hold with equality. And then some calculations will give this number k minus 1 over 2, which means that k has to be odd if there is an intersection between the two maximal independent sets. So the intersection of the two dangerous sets corresponding to a maximal independent set will send k minus 1 over 2 edges to one side and k minus 1 over 2 edges to the other side. And also that, as I said, the bounds here hold with equality, the bounds on this and on those four things. So this will not leave room for this to be anything but 0. So there are no edges coming out from the intersection to the outside of A1 and A2, and nothing from that side of A2 to the other side of A1. So this is how the proof of this proves those two things, by the way, the last two things. It uses a similar type of argument with more things, but I'll not say it, like nothing special there. But the same argument also that was used there as the base case at 5 works here to prove the bipartite and isolated vertex and bipartite. Okay, now recall that we were doing this to be able to do lifts in the proof of Ocripton and Thomason, or if we are trying to use the same kind of argument with connectivity k plus 1. And it relied on that the complement of the lifting graph was disconnected to find a pair of edges that's liftable, but also adjacent in E in the end graph. So as long as the complement of the lifting graph is connected, we don't need to worry, we can do a lift. So we need to think about what happens when the complement of the lifting graph is connected. If the complement of the lifting graph is connected, this means that the maximal independent sets form a connected entity. So one doesn't need to have complete multipartite graph to say the complement is disconnected. If the maximal independent sets don't form a connected entity, even like this, still the complement will be disconnected. So now let's look at what happens when the maximal independent sets form a connected entity. This will happen. The graph G will look like this. So here, this is G. This is not the lifting graph. Any two consecutive, in the cycle case, any two consecutive pairs of a pair of edges will not be liftable, but any two that are not consecutive will be liftable. So where is the maximal independent sets? It's any two blobs of any two consecutive blobs here form one dangerous set corresponding to a maximal independent set. Dangerous because I have k minus 1 over 2 here, k minus 1 over 2 here, and plus 2, so that's all k plus 1. And this is another dangerous set corresponding to maximal independent set, and so on. And the blobs are the intersections of two maximal independent sets. K minus 1 over 2 comes from the thing I mentioned a few pages ago. It's that the intersection sends k minus 1 over 2 here and k minus 1 over 2. So this is an independent set of edges, those two, of size 2, and then another independent set of size 2, and so on. So you can see that the complement of the lifting graph in this case is a Hamilton cycle. Here, the independent sets form a path. So this is one big independent set of size L plus 1, and this is size L. They have to differ by only 1 in this case because of the upper and lower bound. Again, the upper bound of k plus 1 and lower bound of k don't leave much room for anything other than that. And in the middle, there are independent sets of size 2, and these are their intersections. And in this case, the independent sets are arranged in a path, as you see. Those are their intersections. Okay. Okay, so they form a cycle or a path, and anything in the middle will have to be of size 2. Okay. So this generalizes this pattern seen at the beginning of at 4. Here is the independent sets were in a cycle, and here they were in a path. Okay, how do I prove this? It's types of arguments similar to what I just mentioned. So again, we have, for example, 3 independent sets. I'll prove that they cannot intersect like this by taking the dangerous sets corresponding to them and then counting the numbers of edges going between the different parts of the sets of the intersections, or it will be similar to the argument I said about upper bounds, lower bounds of k+1, k, and using the standard equation. But there are numbers like, instead of k-1/2, there will be numbers like k-1/3 and k-1/6 and so on. So, but one can eventually prove that this pattern doesn't occur. And the dangerous sets corresponding to disjoint maximal independent sets can be chosen to be disjoint, and they are arranged in the same way like the dangerous sets are arranged in the same way like the independent sets. And here, okay, if we look at a dangerous set in the middle between two other dangerous sets, its interior here has to be empty other than those intersections, of course. There are vertices in those intersections, but the interior here has to be empty, otherwise we will have a small cut of size k-1, because this set already has many edges coming out from it. k-1/2, k-1/2, and 2, that's already k+1, and it's dangerous. So there can't be any more edges coming out. And so here, any vertices here have only those edges coming to them, and that's at most k-1, that's a small cut, smaller than the connectivity. So there isn't anything here. This says that the independent sets cannot be like this, because there will be dangerous sets corresponding to the 3, and there is nothing here. And also, another way to see it is that S cannot send any more edges in here, because this will not be dangerous then. Yeah. So all these things together say that the maximal independent sets are either arranged in a cycle or in a path. And there is nothing outside the dangerous sets. If I take all the dangerous sets corresponding to all the maximal independent sets, there is nothing outside them. For the same reason, there will be a small cut then. So this roughly justifies those patterns. Okay, I want to mention something else, that k-1/2, as I said before, that appeared in a proof a few pages ago, was with dangerous sets corresponding to maximal independent sets that do not cover everything. I was taking two maximal independent sets that are not both of size exceeding half the degree. But what happens when they are like this, in the case of an isolated vertex plus complete bipartite? Still, one can argue that it has to be distributed like k-1/2 and k-1/2, because otherwise it will, this set will not be dangerous. Back to this figure. Okay, so we know how to lift if the complement of the lifting graph is disconnected. And the case of the complement being connected will not occur here if I assume a connectivity of k+1, because k is odd and k+1 is even. And with even connectivity, the maximal independent sets are disjoint. But this is not the only issue with odd degree or odd size of this cut. There is another issue that after we do all the lifts we can do, we will stop at number 3. Number 3 is always bad with lifting, like it. There, it's possible, if the degree is 3, that no pair of edges is liftable with the other. For example, when G looks like this, any pair of edges, this is a dangerous set because it has only k+1 edges coming out from it. So no pair of edges here lifts with the other, even though this graph is k edge connected. And this is why actually, so there are 2 reasons for why in the proof of Richter and Thomason they deleted an edge here to make this of even degree. It's because they needed to be able to lift all of them, not to stop at 3, which we don't know what to do with, and because the lifting graph, the result of the lifting graph that they used was for even degree. Now we partially know something more, that we know what to do with the lifting graph with odd degree, but we might stop at degree 3. Nothing is liftable. And one might want to think about, where does such a graph come from? there are different graphs at stage 5 that might result in this graph at stage 3. So for example, if the lifting graph is an isolated vertex plus k 2 and 2, like the graph G will be like this, I can lift this and have this, or situation like this. The lifting graph here is k the bipartite graph k3 and 2. And if I do this lift, I'll have this graph again, such that no pair of edges is liftable. Maybe one shouldn't continue lifting until 3. Maybe one should stop at k plus 2, which is odd, and is the smallest degree of S that it's the smallest degree of S that keeps this graph k plus 1 edge connected. Maybe one then should try find a linkage here and try to extend it on the other side, but it doesn't seem to. It seems to be just one step away from a good thing. So this graph is k plus 1 edge connected. So if we take any vertex on the infinite side, there are k plus 1 edge disjoint paths to S, and they will use k plus 1 of those edges. And but they might miss this green one, so maybe the green path will not be able to. We will not be able to make it here. But one might think about, okay, if we do the same thing that was done in the proof of Oak-Richter and Thomason of deleting an edge, the connectivity will go down from k plus 1 to k. And there is no result for finite graphs with k, that's the conjecture. So if we assume the conjecture is true at k, then we have a result in that case at k plus 1 for one-ended infinite graphs. But it assumes the truth of the conjecture. But if we don't assume that the conjecture is true, actually I don't have a result for k plus 1 yet. I thought I do, but I figured out I don't while writing this though. So, but still, assume it's true. Assume we know that for k plus 1 edge connected, one-ended locally finite graphs are k linkable. Assume this is the case, and let's see how to generalize to arbitrary infinite graphs. There are a few results of Thomason from 2016 that might be helpful in this. So first, if we take just any infinite graph, we can first, because this is a finite set, and the graph was k edge connected, we can take a subgraph that's countable and k edge connected. And then countable graphs, Thomason has a result about countable graphs. Splitting here means that each vertex in the graph will be replaced by a set of vertices in a certain way. And the resulting graph, like this operation of splitting as described in the paper by Thomason, we will be able to return the linkage in this graph to a linkage in the original graph. The result is we can break the graph down, the splitting of the countable graph down into pieces like this that are locally finite blocks. Those are blocks. So so edge connectivity is true in each one of them. And if we find a linkage, parts of linkages in here, we can link it with the piece of the linkage in the other one. So we will just focus on one of them, locally finite graphs, but it might have uncountably many ends. Locally finite graphs might have uncountably many ends, like the binary tree. And if you want it to be edge connected, you just add multiple edges. But still, he also had another result in the same paper. So the two results I just mentioned are in a paper by Thomason, different from the paper by Oak-Richter and Thomason. One can break down the locally finite graph if one takes a set like this, like S, the set we were working with, and it has a finite. Suppose it had a finite number of edges coming out from it. Then the outside can be broken down like this into sets of vertices that are have this property of being what he called boundary linked, meaning that the edges happening with it outside, there are rays, they are first edges. So this generalizes the thing that they call the standard fact. There are rays that are in one end even though this thing may contain uncountable ends, that those edges are the beginning of. And then we can repeat the proof we have done before on each one of those pieces. There are only finitely many such things coming out from S. But again, there is a problem with odd degree. And the method they treated odd degree with, if we do it here, will not work. Because deleting an edge from this, deleting an edge from this, and deleting an edge from this will reduce the connectivity by a lot. So we don't want to delete edges in this way. We already know the lifting graph for odd degrees, but we will stop at degree 3, as I said before. So finally, I want to talk about whether the conjecture for finite graphs implies a conjecture for infinite graphs. Again, I will look just at those graphs, that the cases when the complement of the lifting graph is connected, yes, because when it's disconnected, we can do successive lifts. And I will look at an oversimplification of this. I'll contract each blob here into vertex, and I'll assume that I have 2k of them for the moment. So this wall-like structure has to occur, because otherwise we can find a pair of edges to lift. So remember that we found a pair of edges that's adjacent in the end graph and adjacent in the lifting graph. So if there is no such pair, this means that the end graph is a subgraph of the complement of the lifting graph. Being a subgraph of the complement of the lifting graph, in those cases, it means that it's either, okay, I will not talk about this case for now because it doesn't seem nice with connectivity. There are only a few edges below. I'll talk about the cycle. It means that the end graph is a subset of a cycle. So it's either a path or a cycle. So suppose P1 is adjacent to P2, adjacent to P3 in the end graph. This means that there are infinitely many connections between P1 and P2, and infinitely many connections, like clean connections that don't mess with anything else between P2 and P3. So if infinitely many of those connections align, there will be infinitely many connections between P1 and P3 that don't mess with anything else, and this means P1 is adjacent to P3. So the only way for P1 not to be adjacent to P3 is if we have a wall-like structure. If the end graph is either a path or a cycle, we will have a wall-like structure, either like this or a cylindrical wall, but I don't want to draw a cylindrical wall. And this, why did I write the terminals like this? I want them to be all overlapping. S1 T1 overlaps with S2 T2, S3 T3, and so on. Because if two of the pairs of terminals are not overlapping, I can link them on one cycle. There is no problem in using one cycle in linking them. They will not intersect each other. And I can remove that layer or that cycle and do induction on connectivity or something. So I'll assume they are in the worst possible order. That's the worst possible order. All of them overlap. This is a linkage when this situation happens, the worst possible order of terminals and the worst possible structure in the end graph, wall-like structure. And there is a linkage in that case, not just for 11. I just put 11 here, but there is a description for this for general odd K. I will not write it here, take space. Now, suppose we found after contracting the blobs, we found the linkage. Then we expand the blobs again. We will still need to do some work inside the blobs here. Again, oversimplify, and suppose we have only one terminal per blob. So the path that went through this when it was a vertex need to be now done like this. And between the only terminal here and only way for it to go outside without using those is this. So we will need a k+1/2 linkage inside the blob. The blob is k+1/2 edge connected, but this doesn't guarantee the existence of a k+1/2 linkage because we don't know the parity of k+1/2. The conjecture is that for odd k, our connectivity of k is enough, but for even we need +1. So we don't still, so that's even in the case when there is just one terminal. So if there are many terminals, we don't know. Why is a blob k plus 1 over 2 edge connected? It can be seen easily. I mean the middle blobs in the cycle case. This one will be k minus 1 over 2. Because between any two vertices inside the blob, there can only be at most k minus 1 over 2 paths that go out and come back. So there should be k plus 1 over 2 paths between them inside. And also one can, by k edge connectivity, one can see that any vertex in the blob will have k edge disjoint path to the exits, because this is the only way it can link to a vertex outside by k edge disjoint path. So these things might be helpful, but I don't know. Here I want to say that it can't just be a thin wall as the one I drew, because the graph is k edge connected. So probably there's more things here. I don't know how it looks like. Maybe there is enough things to prevent actually the wall-like structure from happening, because this is still something that's not well connected. But yeah, but I don't know how it exactly looks like. So yeah, that's it. So end. That's the end.
Awesome. Thank you so much, Amena. Everyone, let's do a round of applause. If you could unmute, and then I'll count to 3, and then we'll clap. 1, 2, 3. Awesome, thanks. Does anyone have any questions for Amena?
Is there a conjecture where you just have edge connectivity between the terminal pairs and not between other vertices that suffices?
Can you please say it again?
If you just have edge connectivity between the terminal pairs, I don't require the edge connectivity between other pairs of vertices.
Oh, but this will be harder. Yeah, this is a question that was posed before, I think, in the 80s by Okamura, and she did it until size 6, I guess. Yeah.
So is it conjectured? So it is conjectured to work.
Yeah. But it's a harder conjecture. Yeah.
It's a harder conjecture, but presumably it'll be easier for going to infinite things, because then you can just ignore everything else.
It's true.
It's very easy. That is very easy to go from finite to infinite.
Maybe. Yeah. It's true until k equals 6.
Okay.
From the 80s by Okamura.
So you just take the Edge-Disjoint paths between each pair of terminals. That's only going to cover a finite amount of the graph. So I can just throw the rest away.
Sounds good.
Are there any other questions? I guess I was just wondering, so the conjecture that you kind of just assume is true, you must then, I guess, think it can be proved true. Do you know like how to make progress on that, or is that too far away?
The harder conjecture? Sorry?
Yeah, the one you were using.
I haven't thought much about it.
That's okay. Fair enough. Okay, last chance for questions. Okay, I'll end the recording there then. Thanks, Amena.